Hello everyone, my name is Alok Mishra. I am a grad student from Stony Brook University doing my PhD in high performance computing under the advisory of Professor Barbara Chapman. Today I will be talking about extending the LLVM Clang framework for OpenMP Metadirective support, a project done under the collaboration of Stony Brook University and Brookhaven National Laboratory and supported by the ECP project. Before we move on to the meta directive, we are going to be talking about how we are going to use OpenMP in different applications, what are their needs, and how we are basically addressing them in the context of ECP, and how we are working with the rest of the community on doing so. We like OpenMP because it's a de facto standard for several vendors that allow applications to run on different architectures. We are interested in working on the standard that could run on multiple leadership class computing systems, especially in the Department of Energy. Since OpenMP is a bigger standard, it is a great place to work with, but it also has challenges, and we need to understand what's the best approach to express the needs of applications in the context of these challenges to the community. If we look at the top 500 list, over the last few years, we have found that architectures are evolving dramatically in the HPC context. Where we originally had applications targeting multi-core architectures in the early 2000s, but as we have progressed nowadays, we are heading in the context of accelerator type of architectures. And we see that evolution. We also see that OpenMP has kind of responded to that sort of trend. The latest result is that we have support for multiple accelerators, and initially in the mid 2000s, we have support for tasking, and then before that, we support multicore. So OpenMP has been a project that has evolved over time, and its response to the type of architectures that we are supporting. Looking at the roadmap to the exascale system, we definitely like the idea of having a portable programming model. And we see that trend in our architecture as well. For instance, in 2008, we had Jaguar, which was a multi-core architecture. Then in 2012, we had Titan, that was based on GPUs, and there was a big gap for us. And we wanted a directive-based programming model to target that machine. Then in 2017, we had Summit, and by 2022, we will have Frontier. And all of these architectures are based on accelerators or GPUs, and we want to use OpenMP to program them. So why do we need OpenMP? Basically, the applications need it. Basically, the applications need it because they need a programming layer to program the different types of memories available in a node. They needed an API for dealing with data movement, data abstractions, basically a directive that would help to orchestrate the work between the host and the devices. And how can they coordinate and distribute work between them? We have several applications that have been looking at using OpenMP offloading features. Other features of OpenMP like task and thread affinity are also very much needed by several applications. The latest version of OpenMP 5.0, released in 2018, has more than 60 directives. Out of this, variant directive is one of the major features introduced in OpenMP 5.0 specification to facilitate programmers to improve performance portability. The declare variant directive can select a function variant at the call site based on the context or user-defined conditions. Another variant directive, which is meta directive, is the focus of this work. So what is meta directive? By definition, meta directive is an executable directive that conditionally resolves to another directive at compile time by selecting from multiple directive variants based on traits that define an OpenMP condition or context. The mechanism provided by this directive for selecting variant is more convenient to use than any C++ processing pre-processing, since it directly supports variant selection in OpenMP and allows an OpenMP compiler to analyze and determine the final directive from variants and context. The syntax of Metadirective is as shown here, where the clauses is either one of the when clause or the default clause as defined. In the when clause, context selector specification specifies a context selector. In both the when and default clauses, directive variant specifies an OpenMP directive with clauses that apply to it. A meta directive, by definition, is a directive that acts as though it is either ignored or substituted by the directive variant, which is specified in one of the when or default clauses appearing on the meta directive. Whether a particular directive is selected or not depends upon the context selector as specified in the when clause. So, context selectors are used to define the properties of an OpenMP context that a directive or clause can match. OpenMP defines different set of selectors, each containing different selector. The syntax of a context selector specification, as shown here, can be a set of trait selectors. Now, OpenMP defines 4 different trait selectors. The construct selector, the set defines the construct trait that should be active in the OpenMP context. A construct selector which can be an ordered list and comprises of target, teams, parallel, for, and SIMD constructs. The properties of each selectors are the same properties that are defined for the corresponding trait. The device set includes traits that define the characteristics of the device being targeted by the compiler at that point in the program. A device set can have a property such as kind, which specifies the general kind of the device, like host, no host, CPU, GPU, FPGA, etc. The ISA property specifies the instruction set architecture, which is supported by the device and it is implementation defined, while the arc property specifies the architecture supported by the device. The implementation set includes traits that describe the functionality supported by the OpenMP implementation at that point in the program. An implementation set can have a property like vendor, which specifies the vendor identifier of the implementation, or extension property, which specifies vendor-specific extensions to the OpenMP specification. Finally, the user selector, it defines the condition selector that provides additional user-defined conditions. In this research, we exploit this selector to extend Metadirective to support dynamic resolution in runtime as well. For each when clause that appears in a Metadirective, the specified directive variant, if present, is a candidate to replace the Metadirective if the corresponding context selector is compatible with the OpenMP context. So, what is the compatibility rule? A given context selector is compatible with a given OpenMP context if the following conditions are satisfied. First rule, all selectors in the user set of the context selectors are true. Now, this is by the actual definition of Metadirective as specified by OpenMP. We took a cue from Jan's work and extended the user selector to resolve the condition at runtime as well. The next point is that all selectors in the construct, device, and implementation sets of the context selector appear in the corresponding trait set of the OpenMP context. Next, for each selector in the context selector, its properties are a subset of the properties of the corresponding trait of the OpenMP context. Finally, selectors in the construct set of the context selector appears in the same relative order as their corresponding traits in the construct trait set of the OpenMP context. Let us look at an example of Metadirective, where it gives the user the ability to write multiple kernels, each specific for different devices, and the compiler then selects the required kernel during the compilation phase based on the available backend device. In this code, The implementation selector set is specified in the when clause to distinguish between AMD and NVIDIA GPUs. Additionally, specific architecture are specified with the device selector set. In this code, different team constructs are employed as determined by the Metadirective directive. The number of teams is restricted by the num_teams clause, and a thread limit is also set by the thread limit clause for vendor AMD and NVIDIA platforms and specific architecture traits. Otherwise, just the team construct is used without any clause as prescribed by the default clause. Now, some current compilers do provide implementation of OpenMP 5.0 with some limitations, but as far as we know, only the ROS source-to-source compiler infrastructure has partial implementation of Metadirective. Other compilers which claim active development of OpenMP 5.0 specifications are like Cray, where the latest CCE 10 for compiler has partial support for OpenMP 5.0. However, the list of enhancements claimed by the compiler does not include Metadirective. Or GCC 10, which adds a number of newly implemented OpenMP 5.0 features on top of the GCC 9 release, such as conditional last private clause or the scan and loop directives, etc. And they are getting closer to the complete OpenMP 5.0 standard. However, Metadirective is still missing. The Intel compiler supports most of the OpenMP version 5.0 technical report 4 features. So their implementation of OpenMP 5.0 specification is still incomplete, and obviously Metadirective is not yet supported. Now Clang is evolving rapidly under ECP's Solve project and now supports many OpenMP 5.0 features that are essential for ECP applications. These features do not include Metadirective yet, and to the best of our knowledge, our work is the first one which successfully add OpenMP 5.0 specified Metadirective to the Clang framework. In addition to this, we also implement a dynamic extension to the user-specified conditions, which is also defined in the work by Yan and others in the ROS compiler. So what is this dynamic extension? The work by Yan explored a strategy for extending the Metadirective by relaxing its restriction to compile time only selection and allowing runtime evaluation of user-defined conditions. They implemented this in the ROS compiler. We have implemented the same feature in LLVM to establish that dynamic selection of user-defined conditions provides greater flexibility to the users. By definition, all the context selectors in Metadirective need to be resolved at compile time. In this extension, we extend Metadirective to resolve the user condition at runtime. So instead of substituting Metadirective with the given directive variant, we create an if-then-else statement whose conditions will be evaluated and resolved during execution. For this, we parse all the when and default clauses in the Metadirective and create a statement for each of the directive variants specified in the clause. Let us consider a well-known scenario where a programmer is writing a library function to, say, multiply two matrices, where the size of the matrix will only be known at runtime. If the size of the matrices are small, say less than 10, the programmer might want to run the multiplication in serial to avoid parallel overhead. If the size of the matrices are fairly large, say greater than 10 but less than 100, programmers might want to run the computation in parallel while collapsing the two loops on the CPU. But if the size of the matrices are larger than 100 and the code can be built for offloading to an NVIDIA GPU, then programmers might want to offload the computation onto the GPU. Otherwise, they will continue with the parallel execution on CPU. Since the size of the matrix can only be resolved at runtime, there is no way the programmer can use only preprocessing directives to take the decision of which block to compile, and eventually they will end up writing three if-else blocks with different directives. Even if we use the static metadirective code, unfortunately the programmer will only be able to use the metadirective in the last else statement as given in this program, in this code. But with a dynamic metadirective, programmers can write a much cleaner code without replicating the blocks multiple times. One reason why we worked on the implementation of Metadirective was that we needed it for another ECP project of program transformation for automatic GPU offloading with OpenMP, which happens to be the topic of my PhD as well. In this project, we are building a compiler framework to automatically offload profitable region of code to the GPU. For that, we identify parallel regions and suggest multiple variants of the region resulting from optimizations like tiling, interleaving, collapsing, etc., or using different chunk size or thread size on the GPU. We then use a machine learning based cost model to determine the most profitable scenario to offload that kernel. Now, this cost model can return different results. In a simpler case, it can say, okay, this is the best case for offloading and this is the kernel that you should use. Or it could say that for a given parameter, if its value is greater than so and so value, then kernel 1 will be most profitable. Otherwise, kernel 2 or some other kernel based on some other parameter value at runtime. This is where dynamic extension of metadirective will be very useful for us. To test and evaluate our implementation, we used the Summit Supercomputing Cluster at ORNL and the Seawolf Computational Cluster at Stony Brook University. Summit has a hybrid architecture where each node contains two IBM Power 9 CPUs and 6 NVIDIA Volta V100 GPUs. We used GCC version 6.4 and CUDA version 10.1 to build our implementation of LLVM. A Seawolf node, on the other hand, contains two Intel CPUs and 4 NVIDIA Tesla K80 GPUs. We used GCC version 6.5 and CUDA version 9.1 to build our implementation of LLVM on Seawolf. We compiled the three code as shown in our example for matrix multiplication on the Summit cluster to be executed using one NVIDIA V100 GPU. The size of the executables without Metadirective was 199.65 KB. With static Metadirective was 199.66 KB, and with dynamic Metadirective was 199.91 KB. We can observe that the overhead on the size of the dynamic Metadirective is quite minimal. When we ran these executables for varying input sizes, we found there was none to minimal overhead added due to the use of static or dynamic Metadirective, as can be seen in this figure. So for the remainder of the experiment, we only used our dynamic implementation of the Metadirective. So for our experiments, we modified a benchmark application from the Rodinia benchmark suite to use our dynamic Metadirective implementation. We also implemented four micro benchmarks to represent several common methods like matrix multiplication, Gauss-Seidel method, Laplace equation, and Saxby. The Rodinia benchmark suite was chosen primarily because of the diversity of the domain in which each of its applications fall. They are also intended to help the application developers learn how to use dynamic metadirectives in real applications from different domains. All benchmarks were modified to replace pre-processing directives with dynamic metadirective. For each of the application benchmark, we have two codes: the original code with pre-processing directive and the modified code using dynamic metadirective. In our modified code with dynamic metadirective, based on the conditions provided by the user, we generate multiple blocks of code for each if-then-else statement. This will obviously increase the size of our code. In order to assess the impact on the code size, we built both versions of all the benchmark application using our Clang on both Summit and Seawolf. As expected, there is some increase in the size of the executable for our dynamic metadirective implementation, depending upon the size of the kernel which is generated multiple times. But by how much? This figure shows the percentage increase in the size of executable of the original and the dynamic metadirective code. The size of all the executables on Summit are in the range of 70 KB to 980 KB, while on Seawolf they are in the range of 12 KB to 622 KBs. For some applications like BFS, Hotspot, Jacobi, etc., this change is lesser than 0.01%. Hence, it is shown as 0% in the figure. On Summit, the maximum difference is 4.94%, while on Seawolf it is 10.08%, both for the same application k-means. But does using dynamic metadirective affect the actual runtime of the application? To answer this question, we executed both the original code and a modified code 10 times and collected the average runtime for each application. The result can be seen in this figure, which shows the percentage change in the runtime of the modified code when using the dynamic metadirective from the original code. The difference in runtime is almost negligible for all the applications on both the platform, which could easily be caused due to multiple hardware or environmental reasons. On Summit, the maximum difference of the time is 1.76% in SaxPX application, whose runtime changed from 1.705 seconds to 1.675 seconds. Whereas on Seawolf, the maximum change is 2.07% for the same application, where the runtime reduced from 24.443 seconds to 23.937 seconds. Looking at this result, we can conveniently conclude that there is very minimal to no runtime overhead added to the application due to our dynamic metadirective. For future, currently we are working on the first 2 points. We are actively trying to upstream the patch in the LLVM monorepo. We found one bug in our implementation. In the dynamic implementation, for the static case, everything is resolved perfectly. But in the dynamic case, sometimes if an empty directive variant is provided, our compilation crashes. We are looking into it. We have already written several test cases to test our implementation, which is how we found this bug. Rest of the test cases passes successfully. Work is also in progress to integrate this patch to the Solve compiler. In future, as I mentioned in the talk, we aim to use this implementation at automatic code generation for GPUs. We are looking at exploring complex user-defined conditions like calling a function from user condition or using a template for type manipulation. We are also looking at exploring potential pitfalls for downstream code generations. Example, what if we are targeting a wide vector machine that expects to fuse multiple loop nests? Injecting implicit condition statement may reduce the potential to vectorize code blocks. We are currently looking into it. To conclude, we successfully modified the open source LLVM compiler to extend the user-defined conditions of context selectors as used in Metadirective to be resolved at runtime. A dynamic evaluation of user-defined condition can provide more flexibility for programmers to express a variety of adaptive algorithms that boost overall performance. The main advantage of dynamic metadirective is that it adds minimal to no overhead to the user application, with very minor overhead on the size of the code that is generated. You can find our work at the following GitHub location, and the patch for review in LLVM is also put up on the screen. Thank you. Please feel free to contact with any question or suggestions that you have. Thank you.